Po, sir.
Good afternoon sa inyo. So, kumusta yung ating design homework? Nakapag-submit ba lahat?
Yes po, sir.
Actually, kasi hindi ko pa na-checkan yung design homework nyo. So, yun. Kapag na-submit ko naman, kapag na-checkan ko naman siya, then turn in ko agad para makita nyo agad yung grade nyo. Okay? By the way, guys, na-share ko naman sa inyo sa classroom natin last week yung ating timeline after this. So, aware naman tayo na mag-discuss tayo ngayon ng fans and blowers. And after that, we will be having our quiz. So that will be our second quiz. The scope niya is including the discussion natin ng turbines. So lahat ng discussion natin ng turbine regarding sa reaction, yung impulse turbine, plus yung magiging discussion natin for the day regarding sa fans and sa blowers. Okay? And after that quiz, which will be on next week, we will be having our next discussion naman. That will be our last discussion for the whole sem. And that will be for the discussion ng air compressor at saka ng air turbine. Then after that will be our final examination. So basically, we only have 3 weeks left before our final examination. So this week, next week will be our quiz. Then siguro let me introduce next week na rin para hindi naman tayo kapusin ng oras on the other week yung ating air compressor and turbine. And lastly is the discussion nga ng air compressor or ng ating turbine. Okay, so ayun. Konti na lang class, then we can finish our semester. Okay, so for today, our discussion nga will be about fans and blowers. So according to our syllabus, actually yung fans and blowers dapat iwalay na discussion yan. So we have a separate week for fans and separate week for the blowers. Unfortunately, since 3 weeks na lang before final examination, lumipas kasi or nagkaroon kasi tayo ng series of holidays. So medyo hindi tayo naka-cope up. So ang kailangan natin is i-compress na lang yung discussion. And right now, ang i-compress natin is yung the last 2 discussion that we have, fans and blowers, and yung the other week. Okay? So, for the fans and blowers class, for the fans and blowers, ang similarity nilang dalawa is that they are using both air or gases as a medium o yung fluid na dumadaan dito sa fans and blowers natin is air or gases. Okay, so yung difference niya sa nauna nating mga na-discuss, di ba na-discuss natin is pumps, discuss natin is turbine, is that both of pumps and turbines are using liquid or water para sa kanyang medium o yung fluid na yun or yung liquid and water yun yung dumadaan sa pumps and sa turbines. Okay? In contrast, pagdating naman kay fans at saka kay blower, na si fan and blower, air or gases yung dumadaan sa kanya. By term itself, the terminology ng fan and blower, siguro naman familiar na kayo doon, diba? Naririnig nyo na siya. And madalas pa nga, na-encounter natin siya in our everyday use. Electric fan, air conditioning unit, meron yan laging fans, okay? So what else? Similarity naman niya kay pumps. Gusto ko lang siyang i-highlight yung mga similarity natin dito is that fans and blowers, same as pump, sila yung nag-a-add ng energy sa fluid. Remember the function ng pump? Sila yung nag-a-add ng energy sa fluid para ma-move yung fluid from lower point to higher point in the system. Correct? So ganun din pala si fans and si blowers. So sila yung nag-a-add ng energy rin sa air and sa gases. So kung si pumps is using motor to generate or to rotate na yung pump natin, turbine is using generator para makapag-generate ng energy, si fans and blowers are using motor din. Okay? Since parehas lang sila ng energy flow ni pumps, then gumagamit sila ng motor para mapaikot or mapatakbo ang ating fans at ang ating mga blowers. So let's define or let's have a distinct definition or differences ni fans at saka ni blowers. Kasi nga daw, usually, naririnig natin siya as fans or blowers or nagagamit natin sila interchangeably. Meaning, kapag binanggit natin na fan, blower pala yung tinutukoy natin. Pag kapag sinabi natin na blower, fan pala yung dapat na tinutukoy natin. And minsan pa nga, napagsasama natin yung dalawang terminology such as the term na blower fan or ina-assume natin na si fan and si blower ay isang fluid machinery lang or isang machinery lang. But in fact, according to American Society of Mechanical Engineers, define niya si fan and si blower based on their pressure ratio. So what is the pressure ratio, class? It is the ratio daw ng pressure sa outlet and pressure sa inlet ng ating equipment or ng ating machine. So nagbigay si ASME. ASME means American Society of Mechanical Engineers. Sila ngayong organization dealing or doing studies sa different industries, sa different materials, and different processes. Okay? So may binigay na distinct definition or distinct characteristic pala si ASME para ma-define ano pa pag sinabing fans at ano ba yung sinabing blowers. And yung characteristic na yung class is yung sa pressure ratio pala nila. So pressure ratio nga is the discharge pressure over the suction pressure. So doon nagkakaiba pala si fan at si blower. I-define natin yan later on. Okay? Pero yung similarity nila is that both of them are primarily used for cooling and air circulation either in indoor areas, HVAC system, or inside industrial machines as well as electronic equipment. So yun, similarity nila is that most of them are using for cooling and air circulation. Kasi nga naman, air yung gamit natin, di ba? Air yung medium dito. Magbibigay rin tayo later on class ng examples saan commonly used or anong general application ng fan at ng blower para pag nakita natin class, even though hindi natin alam yung pressure ratio niya, makita pa lang natin na, okay, ginagamit pala ito si fan para sa ganitong application, ginagamit na si blower mostly sa ganitong application. So, si fan pala, according to ASME, at yung American Society of Mechanical Engineers, yung kanyang pressure ratio is 1 to 1.11. Meaning, kung yung inlet pressure o yung suction pressure daw ni fan is 101.325, then yung kanyang discharge pressure will be 112.47. So there is a little increase lang sa pressure ng ating air or ng ating gas. Si fan daw is a machine used to add energy to the gaseous fluid to increase its pressure. So nag-i-increase nga ng pressure pero relatively low lang. Up to 1.11 lang or 11% increase. Fans are used then when low pressure nga kasi hindi naman nag-require ng malaking pressure dito, and comparatively large volumes are required. When we say comparatively large volumes are required, meaning yung distribution ng hangin ito class is large dapat yung area. I will have examples for that kung saan siya commonly ginagamit. Okay? So si fans are used when low pressure and comparatively large volumes are required or diffuse yung distribution ng air when it comes to fans. Then same with pumps, ang nakakopol dito na prime mover is motor nga. Okay? So motor minsan, kadalasan pala most of the times ang nagpapaikot sa ating fan, pero sinasabi rin dito na sometimes gumagamit din ng internal combustion engine, pero medyo ano na yun, out of the story na yun, most of the time naman talaga, and as you can see right now, sa ating season, na puro electric motor yung nagpapaikot sa ating mga fans. Then what about the blowers? Kung si fan, ang kanyang pressure ratio as defined by ASME is up to 1.11, for the blowers naman daw, ang pressure ratio niya is from 1.11 to 1.2. So generally, higher than the fans. So kung yung pressure ratio natin, kung yung pressure na pumapasok is around 101.325 kPa plus, then yung lumalabas kay blower is as much as 120 kPa. So blowers can achieve much higher pressure than the fans. Additional functionality or additional application daw ni blower is that they are commonly used to produce negative pressure for industrial vacuum system. So, pag sinabi natin negative pressure sa vacuum, siya is vacuum pressure, and we know that the tendency na yung air natin will move from the lower pressure to a higher pressure, tama? So, ang goal lang pala or ang objective for the blower to create a negative pressure, since ang kailangan nito is mapagalaw yung air from lower pressure to higher pressure, is that yung suction side, okay? So, may tendency pala or may characteristic pala sa blower na ginagamit para magkaroon ng suction. So, we have example for that later on. Ano ba sinasabi na kailangan may suction side or pag-ikot? Yung objective or yung goal ng ating blowers. Okay? So, let's discuss na yung mga common uses or kung saan siya natin madalas makikita general application ng ating fans. So, sinasabi dito class na fans are commonly used sa ventilation and air conditioning, cooling towers, tunnel ventilation, drying, and cooling of materials. So, let's start first with the most common type, with ventilation and air conditioning. So, ventilation and air conditioning class, lahat naman siguro aware na ang ating air conditioning unit, mapa-window type man yan, mapa-split type man yan, merong naka-attach na fan. Tama? Siya yung nag-i-induce ng heat transfer or siya nag-i-induce ng convection. Yung fan na naka-attach sa ating air conditioning unit. So, mapa-split type man yan, merong separate fan sa labas. Kaya nga split type, so nasa labas siya ng bahay. So, merong fan na naka-install doon. At kung naka-install din sa loob ng bahay, meron ding sariling fan. Tapos, yung nakikita natin ngayon sa screen class, yung nasa taas, ito yung nasa taas ng bubong, ng roof, madalas siya makikita sa mga fabrication shop, sa mga manufacturing shop na nag-require ng ventilation, pero hindi naman totally nag-require na kailangan air condition unit yung loob ng ating fabrication shop. Pero kailangan ma-maintain pa rin na malamig or at least safe working place yung loob ng fabrication and manufacturing shop natin. So dapat mag-install tayo ng exhaust fan. Okay? So yung exhaust fan, nagdo-draw siya ng air palabas para ma-maintain na malamig pa rin o yung cool pa rin yung loob ng ating fabrication shop. Since during fabrication, during manufacturing, yung mga machine there, mga cutting works, welding works, grinding works, nag-create yan ng heat load. Okay? And kung hindi mag-install ng ventilation, mag-retain lang yung heat load sa loob ng ating fabrication shop or machine shop or manufacturing shop, in which magiging unsafe naman to kasi nga sobrang init sa mga workers natin and even sa mga equipment na nasa loob. May tendency na mag-overheat. So, nag-install ng ventilation exhaust fan sa taas para ma-maintain or para ma-release yung mga heat load na nandoon sa loob ng ating shop. Okay? Next class is yung ating cooling towers. So kung nakapag-plant visit na tayo, nakapag-site visit na tayo, well, yun yung term, di ba? Instead of field trip, ang term sa engineering is plant visit or site visit. Excuse. Makikita natin or ma-identify natin yung mga cooling towers. Okay, so hindi naman to yung typical na structure ng cooling towers. Iba't iba naman yan. Pero madali siya ma-identify yun. Basta merong fan sa ibabaw. So you can see here, may ibang fan dito sa ibabaw class. So, fan pala yung ginagamit din sa cooling tower. So, ano ba yung purpose ng cooling tower? So, by term itself, cooling. So, siya yung nagpapalamig isa. So, may kita yung mga pipe dito plus. So, nagdadala yan ng mga hot liquid. So, it's either hot water or hot chemical coming from different, kung saan man siya ginila, from industrial, from chemical plant, or kung ano man siya, power plant. Meron lagi tayo na cooling tower. Okay? So, it serves or it acts like condenser. Actually, condenser din talaga siya. So, kung ano yung purpose ng condenser natin, ng nasa aircon natin, mga condenser nun, ito rin yung cooling tower. Parang large scale lang siya. Okay? Kaya may fan din siya, same lang din ng sa air conditioning. Yung mga condenser ng ating split type, may fan din. Siya yung nag-i-induce ng convection or ng heat transfer. Okay, pero may tubig din dito kasi. Nag-draw din to ng tubig from the ocean. Then yun yung nagpapalabig talaga dun sa mga hot water or hot fluid na dala-dala ng pipe. Okay, then syempre, kailangan lang ng additional help from our fan. So hopefully, pag nakita niyo yan during your site visit or during your plant visit, then ma-identify din na cooling tower pala yun. And yung naka-install sa taas niya is fan nga. Okay? Lastly, yung ating tunnel ventilation. Yung nakikita natin sa picture ngayon, class, is sa loob din ng tunnel. Siguro naman hindi tayo makakabisita sa tunnel or magkakaroon ng visit sa tunnel kasi wala naman masyadong activity doon, particularly yung mga mechanical engineering. So, pero whenever there is a job inside the tunnel, hindi lang yung tunnel kasi is considered as a confined space. Kasi sabi confined space as in closed space siya, parang restricted yung ingress and egress mo dito. Yung labas at pasok is restricted. So even hindi lang tao yung restricted, pati yung air, pati yung oxygen na nasa loob ng tunnel, or any closed space man yan, restricted din. Okay? So it's either the mining. For mining, syempre magdidrill din tayo sa loob. So medyo restricted or medyo minimal yung flow ng hangin doon. Yung level ng oxygen mababa. Well, ganoon din sa tunnel. And even other confined space such as tanks and vessel. So tanks and vessel are considered as confined space. And sabi nga, yung oxygen flow doon or yung flow ng hangin papasok sa loob is minimal lang din. Pero paano natin mapapamaintain or may ensure na safe yung working place natin? Okay? So nag-i-install plus during construction yung mga tinatawag na tunnel ventilation in a form of fans. So usually nag-i-install sila at start and at the end ng tunnel. And kung sobrang haba ng tunnel, then may interval yan na dapat merong ventilation. Okay? So ang purpose nga dun is hindi lang mag-supply ng hangin plus. Well, yun talaga yung main purpose niya. But at the same time, during construction kasi, nandiyan yung mga grinding works, mga cutting works, welding works, and iba-iba pa. So hindi lang naman nakatayo yung tao din sa loob ng tunnel. So nagkakaroon din ng mga activity doon. Okay? So during those activity, hindi rin nakakalabas yung mga fumes, hindi rin nakakalabas yung mga dust, mga sawdust, yung mga smokes galing sa mga welding works, mga cutting works, yung mga steel particles kapag nagka-cutting tayo, and kapag nag-grinding tayo ng mga konkreto and ng mga bakal. Okay? So kailangan din ma-circulate and mapalabas yung mga hangin na yun. Kasi kung hindi, yun lang yung malalangkap natin, di ba? So mananatili yun or mag-i-stay yun sa surrounding natin or dun sa workplace natin, which it will cause serious damages sa ating health, particularly sa ating lungs. So kaya kailangan nag-install tayo ng ventilation sa tunnel. And not only tunnel class, repeating ko lang, in every confined space. So those are the common uses, those are the common or general application ng ating fan. So going back to the definition plus ng fan, so they are used when low pressure, since dun sa definition dun sa sample natin plus kanina, wala naman nag-require ng high pressure, tama. So generally, fans are used when low pressure and comparatively large volumes. Large volumes kasi nga, based dun sa sample natin, mostly yung distribution ng hangin through fan is scattered tama. So medyo malaking area yung pinoprovide niya ng air. Okay? So yung disperse ng hangin or distribution ng hangin through or gamit ng fan is medyo malaki yung area na kailangan. Then what about blowers naman daw class? Ano naman ang common uses and general application ng ating blowers? So sinasabi dito na blowers are commonly used during contaminant removal, fume extraction, air handling, material conveying, same with handling of materials, and wastewater treatment. So let's start first with the fume extraction. Based sa definition dito class, they are also used to produce negative pressure for industrial vacuum system. So for producing negative pressure, at tendency nga nito is to ensure na yung flow ng air is from negative going to positive or lower pressure going to higher pressure. So nag-i-induce to ng suction pressure, okay? Or ng vacuum pressure, negative side. So doon natin pwedeng ipasok yung general application niya na fume extraction. So yung nakikita natin pas ngayon is a sample works of welding. Okay, so nasa loob siya ng fabrication shop siguro kasi wala naman direct sunlight. So pag nag-weld tayo, hindi mawawala, hindi natin maiiwasan na magkaroon ng smoke, okay? Fumes. Bakit? Kasi nga tinutunaw natin yung metal, pinag-jojoy natin yung metal, so meron doon na nag-generate na usok or technically high heat. Okay? And if yung usok na yung class, talagang hindi siya magandang langkapin, hindi siya maganda sa katawan, so kailangan siyang ma-disperse, kailangan siyang mailabas sa workstation natin or dun sa fabrication shop. And yun yung function na nakikita natin ngayon. Meron tayo dito na suction side or suction chamber. Okay? So hinihigop niya yung usok na galing sa welding machine, galing sa welder, palabas ng ating fabrication shop and dinidischarge niya yun or dinidispose niya yun siguro sa atmosphere na lang or dun sa labas nga. Okay? So blower pala ang naka-attach dito class. So mga blowers ang ginagamit para makapag-extract ng fumes. Okay, so next example natin class is the wastewater treatment. So kung makakapasyon nga tayo o magkakaroon tayo ng plant visit, if may chance na makapag-visita tayo sa any planta, industrial plant or chemical plant, lagi naman yan na mayroong wastewater treatment. So mapapansin natin to at back, nasa likuran ng ating mga planta kasi medyo may amoy siya. Kasi nga mga wastewater to. So hindi dapat siya naka-install or nakalagay sa harapan lang. So sa mga likod area, sa likodan na part siya na industrial plant nakikita. Okay? So kung nakikita niyo ngayon class, ang ginagawa dito is nagsusupply ng hangin. Yung tubo natin dito or yung mga pipes, yung nagsusupply ng oxygen or ng hangin sa ating wastewater. Okay? So at the end itong pipe natin, is may naka-attach na blower pala. Okay, na yung blower na yun na nagsusupply ng hangin sa ating wastewater. Well, ang goal naman ito class ng advice is that commonly speaking, nagsusupply ko ng hangin or ng oxygen in particular para yung mga bacteria daw na nilagay natin sa wastewater na ginagamit para mag-treat na yung tubig is mabuhay. Okay, so ang tendency nito is parang yung term na aeration, ipoprovide siya ng hangin or oxygen dun sa tubig. So blower pala yung nagsusupply din ng hangin na yun. And lastly class is the material conveying or handling of material. So kung sinabing material conveying or handling of material is nagdadala ng materyales from one point to another point. Okay? From one location, from the source to the discharge point. So paano nangyayari yun? So nakikita natin dito class na merong naka-attach na blower sa baba. Yung blower na yan class, siya yung nasusupply ng hangin para mapagalaw natin or para mapagalaw dito yung materyales from this silo going to this mixing area. Anong example natin dito? So kung makakapunta tayo ng mga batching plants sa extraction ng mga fly ashes, kasi fly ashes ginagamit din sa batching plant kasi that will be used to in lieu or in replacement percentage lang ng mga cement natin, okay? So then later on, ginagawa siya or ina-add siya para maging konkreto. So concrete is a component. Ang component ng concrete is cement, fly ashes, aggregates, sand, and water. Okay? So gawin natin example yung fly ashes. For example, this is a fly ashes class. Sa batching plant naman or any silo or any planta na nagsusupply ng mga ganyan, hindi naman sila manually na kinikilo. That is automatic na. Pumunta tayo pala sa control panel, ito yung required na percentage, required weight, then technically yun ang ipoprovide ng ating silo. Okay? So once na ma-release na dito class yung ating fly ashes, magsusupply ngayon ng hangin ng ating blower para mapagalaw yan papunta sa mixing area. Okay? So it is used, yung blower natin dito is used to convey material such as fly ashes or to handle material from one location going to other location. Okay? So those are the classifications, those are the application ng ating fans and blowers. So sana pag nakita natin class, ma-identify na natin tagad na okay, based from its application, blower pala to at hindi fan. Based from its application, fan pala to at hindi blower. Okay? Kasi nga, commonly, na i-interchange natin yung terminology ng fan yung terminology na blower. Pero stick pa rin tayo class sa definition ni ASME. Kapag yung pressure ratio niya is up to 1.11, then that can be considered as fan. And kapag ang pressure ratio niya is from 1.11 to 1.2, that can be considered as blower. Higher than that, we will consider that as air compressor na. And that one will be discussed next week. Okay? Then what are the typical fan system components? It applies as well to blowers class. So, a fan system component, same lang to kay pumps. Hindi naman totally same kasi syempre si pump gumagamit ng pipe. Kapag kay fans and blowers, gumagamit ng ductings. Okay, pero yung inlet, outlet, motor arrangement niya parehas lang. So yung sinasabi natin na the same lang. Simulan natin plus sa motor. Since si pump na, same lang kay pump, imagine natin, gumagamit din sila ng motor. Yung motor yung nagpapaikot ng sa ating pump. And later on, yung energy na yun ang nag-a-add or yung energy, rotational energy ng pump, yung nag-a-add ng energy dun sa ating fluid. So same din dito kay fans and blowers. We have a motor driven here. So yung motor na nagpapaikot sa ating fan. Okay? Then kung makikita rin natin dito, may naka-attach na variable frequency drive. So it's a separate unit na lagay nyo dito na naka-attach sa motor. So yung main objective ng ating variable frequency drive kung bakit tayo nag-install niyan, by term itself, variable means binabari niya or binabago niya yung speed ng ating motor. Kapag sinabi ko si class na fixed drive or constant speed ang ating motor, meaning kahit ang requirement ng ating system is lower than the capacity ng ating motor. For example, yung capacity ng motor natin is 3,000 RPM. Then for that 3,000 RPM, magpo-produce po ng yung ating fan ng around sabihin natin 300 cubic meters per second na air. Pero what if yung requirement pa ng system natin is lower than that? Example, 150 cubic meters per second lang. Meaning, what if sa area na nag-require ng air, hindi lahat pala yun is operational. We can stop supplying for one area. Pero since fixed drive yung motor, kahit na hindi nag-require ng system ng full capacity, since fixed drive nga siya, magpo-provide pa rin siya 100% continuously, constantly, very constant ng maximum capacity ng air kasi nga fixed drive yung ating motor. Pero kung may naka-install tayo na VFD drive, mababari na or ma-adjust na yung speed ng motor at the same time ma-adjust na yung speed ng fan. At pag na-adjust yung speed ng fan, relative naman to or directly proportional naman to plus sa capacity ng ating fan. So mapapababa niya ang speed at ang volume flow rate ng ating fan. So ano yung advantage nito? Mas makakamura tayo sa power consumption kasi lesser power ang nare-require ng motor in comparison kung fixed drive yun. Okay? So hopefully that's clear. Another thing here is yung ating inlet vanes and ang ating outlet diffuser or ang ating outlet vanes. Okay? So ito yung similarity niya kay pumps. Si pumps meron suction and discharge point or discharge side. Si fan naman, meron din ganun. Ang tawag na sa kanya is inlet vanes and outlet diffusers or outlet vanes. So pareha silang may inlet and may outlet. Pero may variation when it comes to fans. Depending on the requirement daw ng system or sa kanyang application. Minsan merong mga walang suction side, walang inlet vanes. Minsan naman walang outlet vanes. Okay? So, we have a corresponding equations for that. Kung walang inlet vanes, walang outlet vanes, then what will be the effect sa ating total head and later on sa ating power input. Okay? Okay. Any question, class? Before we proceed with our engineering discussion, more on more on narrative lang, more on context lang ng ating fans and blowers.
Wala naman po, sir.
Okay, thank you. So hopefully sana clear sa inyo lahat yun. Hindi ko na define dito class ano yung general classification or yung mga types ng fans and blowers. Kasi nga, kailangan natin makompress yung ating discussion into one session only. So, hindi ko na sinama yung other types, other classification ng fans and blowers. Okay? Let's jump up na sa mga important formulas involved sa ating fans. Okay, so for the engineering part ng ating discussion, so dito na yung ating mga calculation and analysis. Simulan natin sa capacity ng ating fan. Well, madalas naman natin itong naririnig ever since the discussion natin. First day of discussion natin, we heard already the capacity, the volume flow rate. So, term as K lang yan. Area ng fan multiplied by fan velocity. Or kapag binigyan tayo ng area sa suction or sa inlet side, area sa outlet side, then makukuha din natin yung capacity. Yung nga lang relative yun dun sa velocity sa inlet, velocity sa outlet. So area at the inlet multiplied by the velocity at the inlet is equivalent of fan capacity. Or area at the outlet multiplied by the area ng outlet multiplied by velocity sa outlet, makukuha natin yung fan capacity. So yung unit natin dito class will always be cubic meters per second, cubic feet per minute, gallons per minute, liter per second, cubic inches per second, so on and so forth. As long yung in general, unit nito class will be volume over time. Okay? Or volume flow rate. Kung sinabing rate kasi is per time. Ang volume, that is cubic meter, cubic inches, cubic feet, liters. Okay? So, medyo familiar naman tayo when it comes to capacity. Then next is our total head. So kung makikita natin dito class, ang total head natin having two components only, the static head and the velocity head. Hindi na tayo dito class magano ang mag-energy balance. So, ang nawala dito class is yung ating elevation head or H sub C. Kapag fans ang pinag-uusapan natin class, so yung ang component lang ng ating total head will only be the static and the velocity head. Hindi na natin kailangan hanapin pa ang ating hydrostatic head o ang ating elevation head. So when it comes to static head class, ang formula niya is the pressure sa discharge or pressure sa outlet minus pressure sa inlet divided by the specific weight. Ano yung specific weight? So hindi na tayo class dito gagamit ng 9.81 kN per cubic meter. Hindi din tayo gagamit dito ng 62.4 pounds per cubic feet. The specific weight class dito will be the specific weight ng ating air. Kasi yung medium natin dito will be air and not the water. Gumagamit lang tayo ng 9.81 kN per cubic meter and 62.4 pounds per cubic feet kapag water yung medium natin. So, applicable lang pala yan sa pumps and sa turbines. Pero when it comes to fans and the blowers, ang gagamitin natin dito class is the specific weight ng air. The specific weight ng air is the density ng air multiplied by acceleration due to gravity. Okay? Another component class ng total head is yung ating velocity head. So, same lang siya sa pumps and turbines natin. So, velocity head is the difference between the discharge velocity raised to the second power and the suction velocity raised to the second power divided by the acceleration due to gravity. So, medyo common naman to. Walang variation dito when it comes to velocity head. So, VD minus VS lang tayo dito. So, this is the outlet and this is the inlet. G is acceleration due to gravity. Okay, pero generally daw, or most of the times, nagbibigay ng static head or static pressure, ito form of, or as measured by water gauge. So ano ba yung pag sinabing water gauge class? So yung gauge na ginamit natin dito, yung reference is water pressure, okay, o water. But since fan, air yung ginagamit natin, kailangan pa natin i-convert yung water gauge na yun, or yung pressure of water, head of water into head of air or pressure of air. So makikita naman natin yan later on sa problem. Ano ba pa sinabi na water gauge? Okay? Pero yun nga, yung ginamit dito ng pressure gauge kasi nga, for example, sa isang ducting, nag-i-install tayo dito ng isang pressure gauge. Then makikita natin yung pressure doon ng air na dumadaan sa ating ducting. Pero kung yung reference, yung basis o yung measurement ng ating pressure gauge is water, then hindi pa natin siya magagamit directly. Kailangan pa natin siyang i-convert into head of air or pressure of air. Yung conversion factor niya, o yung formula natin dyan plus is density ng air multiplied by head of air is equivalent to density ng water multiplied by the head of water. Okay, so ang hinahanap natin dito class is the head of air. So kung binigyan tayo ng head of water, density ng water is 1,000 kg per cubic meter. Divide lang natin siya sa density ng air. So ito yung class. So ano pala yung density ng air? Yung density ng air, no way na makakalculate natin is 1.2 kg per cubic meter. Pero kung may way naman para makalculate yung density ng air, hindi kailangan natin siyang i-calculate using kung anong binigay sa mga problem. So, ang formula natin dito, class, to calculate for the density ng air is density ng air equivalent to pressure divided by the universal gas constant divided by the air temperature in Kelvin. Okay? So, saan siya nakuha? K from, or it derived from, our universal gas formula, which is PV is equivalent to MRT. So, mass over volume, we know that this is density. Okay? Ano lang natin yan? So, volume. So, density is equivalent to pressure over universal gas constant and the temperature in Kelvin. Okay, dapat yung temperature natin dito, class, will always be in Kelvin or absolute temperature din. So, kung hindi binigay sa problem, saka lang natin gagamitin, class, yung 1.2 kg per cubic meter. Pero kapag nakita natin na binigay si pressure, binigay ang temperature, then makakalculate natin, class, ang density ng air. Okay, so saan ba galing si 1.2 kg per cubic meter? It came from the atmospheric pressure of 101.325 and the atmospheric temperature of 21.2 degrees Celsius. So those two, class, substitute niyan dito, makukuha niyo yung density ng air na 1.2 kg per cubic meter din. So ganun din naman yun. Gagamitin lang natin siya kapag no way na makakalculate natin ang density ng air. Pero kung binigyan tayo ng pressure and ng temperature, then we need to compute first for the density ng air. Okay? So let's go back to the head conversion. Plus kapag binigyan tayo dito ng total head of water, then yung calculate natin dito, class, will be the total head of air. Kapag binigyan lang tayo dito, class, ng static head of water, then ang makukuha natin dito will be the static head of air. Kapag dito is binigyan lang tayo ng velocity head of water, then ang makakalculate natin accordingly is velocity head air. So ganun lang yung class, ha. Kung ano yung binigay sa atin, is it either static, total, or velocity head, then ang lalabas na head of air will be according to dun sa binigay na parameters, is it's either total, static, or the velocity head. So hindi lang naman pag-determine ng total head ang ating ginagawa or ang ating kinakalculate even before. Dinidetermine din natin, class, yung tinatawag na mga power. Okay? So when it comes to fan, ang terminology pala dito is fan power. Meron tayong fluid power, meron tayong water power. Dito naman kay fan, ang term pala niya is the fan power. So fan power is equivalent to the specific weight of air, which is the density multiplied by the acceleration of gravity ng air, multiplied by the fan capacity and the total head of air. Okay? So, familiar naman tayo dito sa equation natin na to. And we are always using this ever since. So, once we calculated already the fan power, ang next na pwede natin makuha, class, is yung ating fan efficiency by dividing the fan power into the brake power. Okay? So, what if binigyan tayo ng motor efficiency, class? So same, hindi ko na siya nilagay dito, class, kasi more on ano naman to, understanding na lang siguro. Motor efficiency is just the brake power divided by the motor power. The overall efficiency or the fan and motor efficiency is equivalent to fan power divided by the motor power. Or the efficiency ng fan multiplied by the efficiency ng motor. Okay? So, same lang din naman to, class, kay pumps. Yung motor natin yung input, then yung output natin is the fan power. So, pabalik, ang energy flow is from motor power to brake power to fan power. Ha? So, mas malaki dapat si motor power in comparison kay fluid. sa fan power natin. But sometimes pala, ang hinihingi is not only the total power, even the static power pinapa-calculate din sa atin. So static power is using static head lang. So kung si total head is using static and velocity head, then the static power is just using the static head. Static head is only this formula class. Okay, so once we calculated for the static power, we can use it to determine the static efficiency, which is the ratio ng static power divided by the brake power. So, if pinapahanap sa atin si static efficiency class, then kailangan natin muna makuha si static power. And after before we get the static power, kailangan muna natin ma-determine yung static head. So from static head, going to static power, going to static efficiency. Ganun din when it comes to fan power or fan efficiency, determine muna si total head. After determining total head, we can determine the fan power. Then after that is the fan efficiency. Okay? We have sample equation for a sample problem for that later on. Makikita natin kung paano ginagamit yung ating mga efficiency, powers, and total head para mas ma-appreciate natin yung ating discussion. Then, ito yung sinasabi ko class na variation kanina. So, kapag binigyan tayo class or kapag nasa problem or we are given a situation na both the suction and discharge duct or both the inlet and the outlet duct natin is available, then to determine the total head, same lang naman, walang mababago, okay? Total head is just the sum of the velocity head and the static head. Okay? So, walang changes kapag both the suction side and the discharge duct is available. Pero what if ang discharge ducting or ang outlet ducting natin is hindi available? So, ito siguro yung mga application wherein nagkakaroon ng extraction ng fumes. Tama? Kasi sa suction side lang siya meron. Pero pagdating sa discharge, wala naman siyang ducting. Directly binabato lang niya sa surrounding area. Yung mga fumes na na-collect niya sa loob ng fabrication shop. So, pag ganun pala class, ang pressure sa discharge outlet or sa outlet ducting natin is equivalent to zero gauge. Meaning, open na siya sa atmosphere. Ang kanyang pressure lang is atmospheric pressure. So, pag ganun yung situation, ang revised equation natin will be this one class. So, total head is just the velocity head plus the pressure ng suction over the specific weight. Kasi nga nag-zero na tayo sa pressure ng ating discharge side o ng ating outlet ducts. Okay? Pero what if naman daw yung ang fan is installed with only the discharge duct? Kapag wala tayong suction side, then our total head is just a function of the discharge velocity squared over 2g plus the discharge pressure over the specific weight. Okay, class. So, ano pa rin naman, depende pa din sa kung ano yung nakalagay sa problema. Analyze pa din natin. Huwag naman nating hanapin lang na yung mga terminology na yan, the fan is installed with only discharge. Minsan kasi hindi lang binibigay yun. So it's up to us na lang kung paano natin mag-designate yung mga given sa problem, then ano yung hinahanap at ano yung approach natin doon. Okay? So analyze pa rin natin yung problem and don't always look for the keywords. Okay, next discussion natin class is the fan affinity loss. Unang beses natin narinig to, yung fan affinity loss sa ating pumps, correct? So kung marirecall natin, we use the term fan affinity loss sa pump to define or to predict the performance ng pump once na binago natin ang impeller diameter or yung rotational speed ng ating pump. So, technically, the same din naman yung ating objective kapag gagamit tayo ng fan affinity loss. So, sinasabi dito class na uh, the, because fans impart velocity and convert velocity to pressure, the flow and the pressure created can be changed by changing the fan impeller diameter size or width and by varying the fan speed by using different size motors and variable drive frequency. So, di ba, same ano lang din naman siya, same lang yung objective natin ng fan affinity loss dun sa ating pump affinity loss. So, sinasabi dito na kapag binago natin plus yung impeller diameter or size, meaning pinalaki natin yung impeller diameter or size, then the flow and the pressure created can be changed as well. So yung flow, related yun sa ating volume flow rate or sa fan capacity. Yung pressure is related to the total head, okay? Hindi lang naman yun, even the power required or power input magbabago rin kapag pinalaki natin or kapag binago natin yung impeller size and binago rin natin yung speed ng motor. So paano ba nababago yung speed ng motor? It's either daw na magpalit tayo ng motor, which is correct. So, pag nagpalit tayo ng mas malaking motor, mas malaki yung rating niya, mas mapapabilis natin yung ikot ng motor. Pero sinasabi rin dito, class, na by installing the variable frequency drive. So, as explained earlier, si VFD nga is ang kanyang main objective is mag-vary yung speed ng ating motor depending sa load requirement ng ating system. Okay? So may tendency talaga na mapababa pa ni VFD yung ikot ng mga motor. So this overall relationship can be simplified with fan equations or the affinity loss. So the fan loss can be used to quickly predict changes assuming the fan diameter and air density are constant. So by the term itself, predict, hindi naman totally precise or accurate yung binibigay ng ating fan affinity loss. Ginagamit lang daw to for us to approximate the changes of speed, size, or pressure with the same fan model or family. So this is just an approximation and not totally accurate or precise yung ating design calculation dito class. So it will be used as a guide lang para ma-predict yung changes ng speed, size, or pressure ng ating fan once na bago natin ang diameter ng ating impeller or ng ating fan or binago natin or replace natin ang motor na ginagamit. Pero hindi lang pala yung class ang pwede natin gawin. Diba? We can change the fan size but maintain the speed ng motor, or we can change the speed ng motor but maintain the fan size, or we can change both of them. Pwede natin palitan parehas yung diameter ng fan at at the same time, palitan din natin yung motor or ibahin natin yung speed ng ating motor. So that is 3 fan affinity loss na lang. Then, we still have one more wherein what is the effect sa performance ng ating fan kapag napalitan din natin yung density ng air. So hindi naman natin generally mapapalitan yung density ng air. So saan ba ito pwedeng mangyari, class? So assume we are using a fan or yung fan natin is designed to operate into an in-house fabrication lang. Okay? But yung density doon ng air is just the atmospheric density. What if yung same fan na yun plus, itatry natin siyang gamitin or i-install sa underground or sa mining area? We know that the density will vary according to pressure, according to temperature, right? PV equals MRT. So mass over volume is equivalent to pressure over temperature. So once nag-vary yung pressure or once nag-vary yung temperature, accordingly, pagbabago rin yung density. So from the industrial area, nilipat natin siya into the mining area wherein yung temperature siguro mas mainit, yung pressure siguro mas mababa. And definitely, yung density ng air doon is mas magbabago rin. Okay? So comparing those two, what will be the effect ng density na yon, density changes sa um, power input and sa total head ng ating fan. So yun din ang verify natin using affinity loss. As I said earlier class, we have 4 sets of affinity loss here. So please, it's up to you na lang kung paano nyo i-memorize yung 4 sets na yan. Kasi medyo madami na, pero yun yung 4 times 3, 12 agad yan. Para hindi tayo malito, okay? During final examination, inuulit ko lang, during board examination, wala tayong references. Bawal ang merong notes na ginagamit during those exam. Okay? So dapat talaga na memorize natin yung ating mga equations. So start muna natin class dun sa ating variable speed and constant diameter. So ito nga yung kapag nagbago yung ating rotational speed and maintain natin yung constant diameter, ano yung gagamitin natin equation to determine or to predict the performance ng ating fan. So the first one is it states that it tells us that the change in airflow rate of a fan is proportional lang sa change ng speed ng ating propeller. Meaning, kapag daw binago natin yung speed by 20%, yung volume flow rate o yung fan capacity will change by 20% as well. Okay? So that is directly proportional lang class. And for the second one, if we change the change in total static pressure ng ventilation system will increase by the square of the change in propeller speed of the fan. It's just H1 over H2. It's equivalent to N1 over N2 squared. So parang nasa 44% ata yung change nito kapag yung rotational speed has increased by 20%, parang naka 40% ata yung increase nito class. Check ko lang na. Well, ano lang naman to, general assumption lang. Correct. So nasa 44% yung magiging increase ng ating total head kapag yung rotational speed class has been increased by 20%. Wherein the change in horsepower required by the fan to turn the propeller will increase by the cube of the change in the propeller speed of the fan. So numerically, so check natin kung ilan yung mababago. So magkakaroon ng 72.8% increase pala ng power requirement or power input kapag binago natin yung speed ng ating fan by 20%. So dito class, initially, it's just directly proportional. So kung nag-increase tayo dito ng 20%, kung ang N2 natin has been increased by 20%, then our Q2 or fan capacity will increase by 20% as well. Ating total head will increase by around 44% and our power required or power input will increase by around 72.8%. So yun yung variation niya, yun yung magiging effect or magiging performance ngayon ng ating fan kapag binago natin yung speed pero maintain natin yung diameter. For the rest class, kaya na siguro yung mag-analyze ha. Sa ano lang naman to, nilagay ko na siya sa context or into words para mas madali nyo maintindihan. Okay? So for the rest, we have a constant speed and variable diameter. So kaya na siguro ang mag-analyze nito class. Pero ito yung equation niya. The next one is kapag parehas natin binago si speed and parehas natin binago yung propeller diameter. And the last one is kapag binago naman natin yung density. So kapag binago natin yung density class, yung fan capacity pala is hindi nagbabago. So whatever the density man yan ng hangin, the fan capacity will remain the same. Kaya na tayo Q1 is equivalent to Q2 lang. Pero yung pressure class and total head will vary accordingly or directly proportional yung changes. Meaning kung 20% yung changes in density, yung ating total head will increase by 20% as well. Kapag yung density natin is nagbago by 20%, yung ating total power required is has been increased by 20% also. Okay? So, any question class before we move with our example problem?
Wala pa naman po, sir.
Thank you, Ms. Claudine. So, for example 1.0, let's try to use most of the equations here. We have two sample lang class sa fun. Then the rest, jump up na tayo sa blower. Okay? So, for example 1.0, we will try to use all of the equations na discuss natin kanina. So, except lang yun kay affinity loss. Sa example 2.0, saka natin gamitin yung ating affinity loss. Okay? So, basahin muna natin. Example 1.0, a fan draws 1.42 cubic meters per second. So, the problem gave us already the fan capacity or the volume flow rate of 1.42 cubic meter per second. So, the static pressure, 2.54 centimeter of water. Ito yung sinasabi ko class, minsan, binibigyan na tayo ng pressure, pero ang unit niya is into water. Okay? Yung reference ng measurement ng pressure na yun is based from water gauge. Kailangan natin siyang i-convert later on into head of air or pressure of air. So we have given a static head of water of 2.54 centimeter through a duct 300 millimeter diameter and discharges it through a duct of 275 millimeter. So the problem gave us the inlet and the outlet duct of 300 millimeter and 275 millimeter diameter respectively. So define the static fan efficiency. So yung pinapahanap sa ating class is the static fan efficiency. If the total mechanical is 70% and is measured as 25 degrees Celsius and 760 millimeter Hg. So what is 25 degrees Celsius plus and 760 millimeter Hg? So ito class yung ating atmospheric condition. 25 degrees Celsius is our temperature ng air or atmospheric temperature ng air and 760 millimeter Hg is the pressure. That is the atmospheric pressure or the barometric pressure. Okay. Ano naman plus yung ating 70% na efficiency dito? The total fan mechanical efficiency of 70%. Wala naman tayong binanggit na ganyan kanina. Pero please remember class na whenever we are discussing mechanical, pag may term na mechanical, lagi siya related kay brake power. Okay? So yung binigay sa problem, the total fan mechanical, which is 70%, that is already class the fan efficiency. Wala rin naman tayong ibang efficiency dito class kasi yung hinahanap nga is the static fan efficiency. Okay, so leaving us with the fan efficiency yung 70%. So convert muna natin class yung ating static head of water into static head of air using this equation. Static head of air is equivalent to static head of water multiplied by the density ng water divided by the density ng air. So, static head of water is 2.54 centimeter. Convert na natin yan sa meter later on. Density ng water is 1,000 kg per cubic meter. Constant naman yun. Density ng air is hindi binigay class. And sabi ko nga, kung hindi siya binigay, and no way na makalculate natin siya, then saka lang tayo gagamit ng 1.2 kg per cubic meter. Pero binigay kasi sa problem class yung air condition or yung condition ng ating atmospheric air which is 25 degrees Celsius in temperature and yung pressure is 760 millimeter Hg. So kung titingnan natin class, ang density ng air is equivalent to pressure over gas constant over the air temperature, meaning makakalculate pala natin ang density ng air. Okay? So ito lang naman yung task. So yung pressure natin is 760 millimeter Hg. So yung conversion factor niya is that for every 760 millimeter of mercury, there is 101.325 kPa. Meaning pala, this 760 millimeter of mercury is just the atmospheric pressure talaga. Equivalent lang siya kay 101.325 kPa. And divide lang natin siya sa universal gas constant of 0.287 kilonewton meter per kilogram Kelvin and the temperature ng air 25 degrees Celsius converted into Kelvin or absolute temperature. So let's cancel the unit, Kelvin into Kelvin, kilonewton, kilonewton. It will give us, this is meter, then it will be cubic meter. Density ng air of 1.1729 kilogram per cubic meter. Okay, so once you already know the value of the density ng air, makakalculate na natin class ang static head of air. So we know already the static head of water, the density ng water, density ng air, then one unknown, one equation we can calculate for the static head of air, which is 21.6557 meters. Okay, class. Pero yung hinahanap kasi dito is the static efficiency. So, babalikan natin yung equation natin. To determine the static efficiency, kailangan natin ma-determine muna si static power at si brake power. Yung static power, we can determine using these equations. Specific weight ng air, which is we know naman already. We have the density ng air and acceleration due to gravity times the fan capacity and the static head. Nakuha na natin kanina si static head, then madidetermine natin yung nasa numerator, which is the static power. So, ang kulang na lang class is yung ating brake power. So, natin pwedeng kunin si brake power. We can get the value of brake power using the fan efficiency. The problem gave us the fan efficiency of 0.7 or 70%. Then we can get there the brake power. Ang kailangan lang natin makuha class is yung value ng fan power. Medyo mahaba ito class ha, pero nasolve na rin naman siya, kaya mabilis na. Pinapaliwanag ko lang sa inyo kung paano natin makukuha yung ating static efficiency. So from that fan power, kailangan natin muna makuha yung ating total head. Yung total head natin is just the sum of our static head, wherein meron na tayong value, and the velocity head. For the velocity head, wala pa tayong velocity ng discharge and velocity ng suction. Pero we know naman na using the capacity, we can determine the velocity accordingly. Correct? So, check lang natin yung binigay na area o diameter ng ating ductings. Then, divide lang natin siya sa fan capacity at makukuha na natin accordingly ang velocity ng suction and velocity ng discharge. So once we have the velocity ng discharge, velocity ng suction, makukuha na natin yung total head class. After getting the total head, madidetermine natin ang fan power. After determining the fan power, makukuha natin yung brake power and makukuha natin ang static efficiency. Okay, so almost all of the equations dito na discuss natin is na-tackle natin class sa example 1.0. Okay, so as I said earlier, kailangan natin ma-determine muna si static power. So static power is a product of the density ng air, 1.1729 kilogram per cubic meter. Acceleration due to gravity, which is 9.81 meter per second squared. Ginawa ko lang siya dito conversion factor class para ma-cancel to. Multiply by the fan capacity of 1.42 cubic meters per second and multiply to the static head of air, which is 21.6557 liters. So it will give us a static power of 0.3538 kilowatts. Okay, so next, determine naman the velocity head by determining first ano yung value ng velocity ng discharge and velocity ng suction. The problem gave us already class the diameter ng inlet or diameter ng suction, diameter ng outlet or diameter ng discharge, and the volume flow rate, which is 1.42 cubic meters per second. So accordingly, makakalculate natin class ang velocity ng discharge and velocity ng suction. Remember Q equals AV. So V equals Q over area, which is pi d squared over 4. So we have here the values ng suction and values ng ating discharge. Then let's calculate for the velocity head using this equation class. We already have the velocity ng discharge, velocity ng suction, and acceleration due to gravity. So we can determine the velocity head. I-add lang natin siya class sa ating static head, then makukuha na natin ang total head. So that will be 30.198 meters. So after getting the total head, multiply lang natin siya sa specific weight and fan capacity, then we can determine the fan power, which is 0.493 kilowatts. And equate that sa given na fan efficiency, then makukuha natin yung brake power since one equation, one unknown. Brake power is equivalent to 0.7048. Okay. Then since we already know the value of the static power, 0.3538, we know the value of the brake power, 0.7048. Then multiply lang natin siya sa 100. Divide natin sila sa isa't isa, multiply by 100. Then we can get the value of the static efficiency of 50.1948%. Okay? So based dun sa ating discussion kanina, nagamit natin yung capacity, velocity head, static head, the total head, the head conversion class, the formula to determine the density ng air, the fan power, fan efficiency, static power, and the static efficiency. Okay, so almost lahat ng equations natin class is nagamit natin here in example 1.0. Any question class? Before we move with our second example.
Wala naman po, sir.
Okay, thank you. Thank you. Okay, so class for example 2.0, this is a great example. Gagamit tayo dito ng affinity laws, pero this is a close to reality example since binigyan tayo ng scenario wherein pinapadetermine sa atin kung ano yung magiging changes or ano yung restriction din na meron dito sa situation natin dito. So the customer daw is requiring or desiring more airflow but doesn't want to increase the size of the fan. Kasi nga, this happen often in process ventilation system redesign where the cost of changing the ductwork limits the option for increased airflow to changing the propeller speed. Since ang dalawang way class, actually tatlo nga yan di ba? Or apat na way pala sa fan affinity laws. May apat na way tayo para mabago yung fan capacity. Either palakihin natin yung diameter ng fan, pabilisin natin yung diameter ng fan, palakihin natin yung diameter ng fan, and pabilisin yung ikot ng fan. Pinagsama natin yung option 1, option 2, and baguhin yung density. So, sa option 1, pabilisin natin or palakihin natin yung diameter ng fan. Hindi siya considered sa option kasi once na binago natin yung diameter ng fan, those ductings na naka-attach sa fan natin, sa inlet and outlet ducting, kailangan din natin baguhin. So we need to install new set of ductings which is equivalent, naka-equate siya sa cost, hindi nga siya option ng ating customer. Kasi may cost involved, medyo magastos yun kasi magkakaroon tayo ng reinstallation, magkakaroon tayo ng redesign ng ductings natin. So, the option 1 is not applicable. The option 3 won't be applicable as well kasi yun nga yung combination na papalitan mo yung size at the same time papalitan natin yung speed. Hindi nga natin pwedeng palitan yung size. So, the option 3 won't be applicable as well. Yung option 4 na papalitan natin yung density, mas hindi siya applicable, di ba? Mas hindi siya option and hindi siya feasible. Paano naman natin gagawing palitan ng density ng air? So yung applicable na lang dito, class, is to increase the airflow, correct? By changing the propeller speed. So kailangan natin pabilisin na lang ang ating propeller or bilisin yung ikot, rotational speed ng ating motor or ng ating fan. The exhaust fan daw were moving 15,000 cubic feet per minute of air with a propeller speed of 1,000 RPM. So yung propeller speed pala is running at 1,000 RPM and providing around 15,000 cubic feet per minute. And gusto nga ng customer natin na pataasin pa yung value ng ating CFM or ng ating volume flow rate. The exhaust fan motors were rated at 1,750 RPM. And kung makikita natin, class, yung rating ng motor is much relatively higher compared dun sa actual rotational speed ng ating fan, which is 1,000 RPM. So considering losses, actually medyo malaki pa rin talaga yung difference nila. So pwede pa nga natin pabilisin yung speed ng ating fan. Okay? Pero paano natin gagawin? It was given here as well na yung motor daw natin is rated at 5 HP. Pero yung peak lang niya is 3.75. Ano ibig sabihin nun? So kahit na yung rating ng motor natin is at around 5 horsepower, yung nagiging power consumption lang o yung peak lang ng ating motor is around 3.75 HP. Meaning meron pang 25% or around 1.25 na hindi nagagamit o hindi na-utilize ng ating fan. May 25% pa capacity yung ating motor na hindi nagagamit. Kasi hanggang 3.75 lang yung nagagamit during the operation. The air supply to the building was through louvers with static pressure of 0.15-inch water gauge. The customer didn't want to increase the negative static pressure in the building. So how much air can each fan provide if they were only to change the shield sizes in each fan? So yung shield sizes class is just the pulley. Okay, ito lang yung pulley natin, termed as shield lang. So babaguhin lang natin yung shield size para mapabilis yung speed ng ating fan or ng ating propeller. Iba-maximize lang natin class from 5 horsepower to, from 3.75 horsepower going to 5 HP. I-utilize natin yung remaining na 25%. Okay? So, what will be the effect of the 25% increase dun sa magiging panibagong volume flow rate? Yun ang kakalculate natin yung class. Okay, so let's continue. Determine the new speed of the fan by increasing the power from 3.75 HP to 5 horsepower. So based from our affinity loss, let's go back to our fan affinity loss. Meaning, ito yung kukunin natin sa variable speed, and constant diameter. Since ang option nga lang natin is baguhin yung speed ng fan and i-maintain ang diameter ng ating fan. So ito yung gagamitin natin to determine or to predict the new fan capacity and new fan rotational speed. Since in-increase natin ang ating power from 3.75 HP to 5 HP, that is 25% increase, what will be the new rotational speed? Yun ang magiging tanong natin. So the new rotational speed based from our fan affinity loss will be 1,100 RPM, and that will be 10% increase plus. Okay? So check natin, 1,000 cube times 5 divided by 3.75. Okay. So that will be a 10% increase from the previous rotational speed of 1,000 RPM. Okay. Then what will be the effect naman daw niyan plus sa ating panibagong flow rate? So ito yung tinatanong sa problem. How much airflow can each fan provide? So from the original 15,000 cubic feet per minute, then we increase this RPM by 10%, 1,100 RPM. Then what will be the effect to the fan capacity? So based from our fan affinity loss, kung titignan naman natin dito class, that is just directly proportional. Q1 over Q2 equals N1 over N2. Then directly proportional nga, then we will be having as well a direct 10% increase sa ating fan capacity. Okay? So from 15,000, nag-increase yung ating fan capacity into 16,500 CFM. So from 25% na increase in power, nagkaroon tayo ng increase plus na 10% in volume flow rate or fan capacity. Okay, then lastly, from the fan affinity law, the impact of additional air flow into the customer building would result in an increase in static pressure. So from 0.15 inch water gauge, nag-increase yung ating static pressure na or until 0.1815 inch water gauge. Okay? So, hindi naman tayo nag-reduce class ng pressure, rather nag-increase pa nga yung pressure natin. Okay? Since the customer didn't want to increase the negative static pressure in the building. Unfortunately, nag-increase tayo dito ng pressure class. Okay? Pero yung hinihingi talaga sa problem is determine the new flow rate, meaning ang nakuha natin class is 16,500 cubic feet per minute or the 10% increase. Okay? So, any question with that class? For example, 2.0, ginamit natin ang ating affinity loss. Siyempre, hindi natin gagamitin lahat. Medyo matagal-tagal naman yun. Pa-analyze na lang class or pa-memorize na lang yung fan affinity loss natin para kapag nakita natin sa problem, ano yung condition na sinasabi sa problem, accordingly, alam natin kung anong affinity loss yung gagamitin. Okay? Any question class? For example, 1.0 and 2.0?
Wala naman po.
Okay. Sige class, ano lang muna tayo. Since lowers na yung kasunod natin, let's have a 10 minutes break. So let's meet at around 3:45. 10 minutes break muna tayo class ha. Kahit CR break muna tayo. Thank you. Yes, class. Continue na natin para matapos tayo ng maaga. Okay? So, we have few more slides remaining. Blowers na yung di-discuss natin. And we only have 3 exercises or remaining problem sets regarding the blowers. So, for the blowers class, yung nakikita natin dito class is yung ating isentropic. Kasi wala. Okay, this is isentropic question. Adiabatic or isentropic work. Okay? So ito yung naiba when it comes to funds. Pero hindi lang naman to class yung applicable dito. Basically, yung lahat ng naging discussion natin, hindi naman totally lahat, yung naging discussion natin regarding sa funds, the capacity, the velocity head, the static head, the total head, the power, the efficiency, magagamit natin yan sa blowers. Okay? Blower efficiency, the blower power, the capacity, velocity head, static head, total head conversion, pagkuha ng density ng air, magagamit natin ito class sa blower. We have example 3.0 later on para makita natin yun na applicable din pala siya when it comes to blower. Yung na-add nga lang sa kanya is itong ating tinatawag na adiabatic or isentropic work. So bakit tayo nagkaroon class ng adiabatic or isentropic work? Kasi si blower, by definition, di ba, si blower is a machine na nagko-compress. So relatively higher na yung pressure nito when it comes to or in comparison niya kay fan. So yung compression ng ating blower, once na nag-increase yung pressure natin, accordingly, nag-i-increase din yung ating or nagko-compress din yung ating volume dito class. So if this is our pressure, then yung volume ng air is relatively nag-compress din. Okay? Since may compression dito class, merong adiabatic or isentropic compressions involved, yung gagamitin natin na pag-determine ng work is yung kanyang adiabatic or isentropic work related to class sa ating thermodynamics previously. Pero hindi natin siya dinerive, ito na lang, so i-memorize lang natin yung ating work formula involved para sa adiabatic or isentropic work. Sinasabi din pala dito na the blower is usually based upon either an adiabatic or isothermal compression. Pero yung gagamitin lang natin ngayon is the adiabatic or isentropic work. Okay? So adiabatic means no transfer of heat. Perfectly insulated. So, ang equation natin to determine the adiabatic or isentropic work class is the K over K minus 1. So, what is the meaning of K? K here is what we call the specific heat ratio or the ratio of the specific heat at constant pressure to the specific heat at constant volume. So, the specific heat at constant pressure and specific heat at constant volume class, ito yung properties ng ating air or properties ng gas. Magbavari to depending sa kung ano yung temperature or operating temperature ng ating air. Kung hindi siya binigay sa problem task, I would suggest na gamitin natin yung typical 1.4. Pero kung binigay sa problem, then disregard na lang natin si K 1.4. Okay? Pag hindi lang siya nabigay sa problem. And specific heat, sabi ko nga, specific heat at constant pressure, specific heat at constant volume, madidetermine natin yan plus sa table nga ng properties. Pero hindi natin siya doon i-verify or pagbabasihan. So it's either ibibigay na lang siya directly or let's assume or let's use the K value of 1.4. Okay? Pero talagang merong properties specific yung air at a certain temperature. Okay? Doon natin i-base talaga yung ating specific heat ratio. So, continue lang natin, adiabatic or isentropic work is K over K minus 1 multiplied by the absolute pressure at the inlet and the flow capacity. Yung P natin dito class is pressure at the inlet and that must be in absolute pressure. So, unlike here in determining the static head, wherein yung pressure na gagamitin natin dito is gauge pressure or gauge pressure na discharge or sa outlet, gauge pressure sa suction. When it comes to adiabatic work, ang gagamitin natin class is absolute pressure. Pwede naman natin gamitin dito class is is absolute pressure din. Both side nga lang, i-add natin yan ng absolute pressure or 14.7 PSI or 101.325 PPA. Okay? Ika-cancel out din naman nila yung isa't isa. Say, you will add 14.7 here, you will add 14.7 here, di ba minus ko rin naman, then they will just cancel each other out. So usually, ginagamit na lang natin siya na gauge pressure. However, when we are discussing about blowers and adiabatic work yung gagamitin natin equation, lahat ng pressure na nakikita natin dito, classic, is dapat naka-absolute. Okay? So, multiply natin it into the ratio ng ating outlet pressure and into the inlet pressure. So, both of them still is in absolute pressure. Raise to K minus 1 over K, then subtract natin into 1. So, that will give us a value of watts or kilojoules per second. So even though work, yung definition natin dito class, ang makukuha nating unit dito must be lagi in kilowatts. Okay? Kasi yung ating flow capacity is naka-second siya. Kasi nga siya is volume flow rate or cubic meters per second. So makukuha nating unit dito lagi class is dapat naka-kilowatts or pound-foot per minute, pound-foot per second. Then later on, mako-convert natin into horsepower. Then accordingly, class, pwede din natin gamitin yung ating second equation. So, ang naiba lang dito class is the term MRT. So, based from ating universal gas law, PV is equivalent to MRT. So yung ating pressure at the inlet multiplied by the volume flow rate. So ito na yung P multiplied by the volume. Flow rate nga lang siya. Then equivalent siya sa ating mass flow rate multiplied by the gas constant and the temperature at absolute temperature as well. So ito lang din yun class. Ang na-add lang natin dito is yung ating term MRT1. Okay? So that must be the temperature at the inlet also and absolute temperature din dapat yung gagamitin. Then as I stated earlier, hindi lang naman si adiabatic or centropic work yung pwede nating ma-determine when it comes to blowers. Now, what if hindi binigay yung K value? What if hindi binigay yung pressure at point 1? What if hindi ganito yung ating equation? Okay? Or no way na magagamit natin to. Then we can also use our general equation, specific weight, multiply by the volume flow rate, multiply the total head or adiabatic head. And the same, that will give us kilowatts. Okay? And lastly, determining the efficiency ng ating blower. In determining efficiency ng blower natin, we have only two efficiency here. The mechanical efficiency, which is the isentropic work divided by the brake power. So, para lang to class na blower efficiency. Okay? Ang term lang niya dito is mechanical efficiency. So, isentropic work, makukuha natin yan sa adiabatic or isentropic work equation. And our general equation, specific weight multiplied by volume capacity and total head. I-divide lang natin siya sa brake power, then makukuha na natin ang mechanical efficiency or ang ating blower efficiency. Then we are given here additional efficiency called the actual blower efficiency. So wala mo na akong nakita ng ganitong problem class, pero what if binigyan tayo ng actual work and pinapahanap na sa atin yung actual blower efficiency. Then divide lang natin yung na-determine natin na isentropic work sa actual work, then makukuha na natin ang actual blower efficiency. Okay? And the overall efficiency is just the product of the two. Mechanical efficiency and actual blower efficiency. So, gamitin natin to class sa following problems. So, hopefully, ma-appreciate natin yung discussion natin sa blowers using this following example lang. So yung example 3.0 class, hindi tayo dito gagamit ng adiabatic work or the isentropic work. Rather, gagamitin natin dito yung mga discussion natin nung una, in determining the total head, velocity head, the static head, using the specific weight, volume flow rate, and total head in determining the blower power. Okay? So, i-correlate lang natin yung binigay nating equations. Important formulas related dito class dun sa example natin ng blower. Kasi same lang din naman yung kanilang process. Nagkaroon na ng compression si blower, kaya nag-introduce tayo doon ng adiabatic work. So for example 3.0, a small blower handles 44 cubic meter per minute of air. So the problem gave us the volume flow rate of 44 cubic meters per minute, whose density is 1.169 kilogram per cubic meter. So the problem gave us the density as well. The static and velocity head, so binigyan tayo ng static and velocity head of 1,605 Pascal and 120 Pascal with water as the gauge fluid. Yun nga lang, ang binigay sa ating pressure dito class is, ang reference niya is water gauge. So i-convert natin yan dapat into pressure of air or head of air. So the temperature is 15.56 degrees Celsius, respectively. The local acceleration is 9.741 meter per second squared. So medyo add to kasi binigyan tayo ng separate or ng local gravitational acceleration. Pag sinabing local gravitational acceleration class, meaning nag-occur lang to dun sa specific na location. So hindi to applicable in general. Kaya nga siya local gravity acceleration lang. Okay, so for this problem lang, specific natin gagamitin yung 9.741 meters per second. So pinapahanap sa atin is determine the power input to the air from the blower, and if the initial velocity is negligible, find the final velocity. So let's focus muna dun sa ating first question, find the power input to the air from the blower. So based from the equation plus ng blowers, let's just copy paste all of this. Check natin kung ano yung magagamit natin dito. Okay, so did the problem give us the K value? Hindi, di ba? Pero as I said, pwede natin gamitin dito later on is 1.4. Kung hindi naman tayo binigyan, we can use 1.4. Okay? Did the problem gave us the pressure at the inlet? However, hindi tayo binigyan ng pressure at the inlet. Ang binigay sa atin class is the static head already. The static head, by the equation, it's already the pressure ng discharge minus the pressure ng suction lang. So that is the static head. So hindi niya ni-specify what is the pressure ng discharge and what is the pressure sa suction. So generally speaking, we cannot use this equation in determining the power input to the air from the blower. How about this one class? Do we have the K? As I said, we can use 1.4. What about the mass flow rate? Unfortunately, actually we can get the mass flow rate here class eh. We have the volume flow rate, we have the density. So we can get or we can determine the mass flow rate using that. Okay, density is equivalent to mass over volume. We have the volume, we have the density, then we can determine the mass flow rate. Okay, however nga lang, hindi nga tayo, temperature class binigyan tayo 15.56 degrees Celsius. So basically we can use that kung binigyan tayo ng pressure na outlet and pressure sa inlet. However, hindi rin tayo binigyan both ng pressure sa discharge and pressure sa inlet nga. Ang binigay lang sa atin is the static head na. So static head, that is PD minus PS na. Okay, so no way na ma-determine natin what is the value of the discharge pressure and what is the value ng suction pressure. So for that, eliminate natin itong equation na to. So leaving us with this equation to determine the power input to the air from the blower. So ang kailangan lang natin makuha dito class is the total head. Kasi we have the density already, so makukuha natin ang specific weight. And we have the volume flow rate which is 44 cubic meters per minute. So convert muna natin class yung static head and velocity head in water gauge going to head of air or total head of air para may substitute yan natin dito sa class. Okay? Since binigyan tayo class in Pascal, so 1605 Newton per meter squared for the static head of water and 120 Pascal or 120 Newton per meter squared for the velocity head ng water. Para ma-convert natin siya into meters of water, i-divide lang natin siya sa specific weight ng water. Okay, yung specific weight ng water is acceleration due to gravity times the density ng water. So 1,000 kg per cubic meter times the acceleration due to gravity of 9.741 meters per second squared will give us Newton per cubic meter. So cancel lang natin yung unit. It will give us 1 unit of meter here. So yung value pala ng static head ng water is equivalent to 0.1647 meters. Sa ganun din class sa ating velocity head ng water, divide lang natin ang 120 Pascal into the specific weight ng water. So it will give us 0.0143 meters. Let's add them both para makuha natin yung total head ng water. So the total head ng water is 0.177 meters. Then using this equation, density ng air multiplied by the head of air is equivalent to density ng water multiplied by the head ng water. Okay, we have the density ng water, 1,000 kg per cubic meter. Total head ng air, ng water is 0.177 meter. Density ng air, binigay sa problem as 1.169 kg per cubic meter. Then we can get the value of the head of air as 151.4 meters. Then we can substitute it here to determine the power input to the air from the blower. Okay, so by calculation, the power input to the air by the blower is 1.264 kilowatts. Okay, class, clear ba yun? Next na hinahanap is, okay, thank you. So next na hinahanap is the final velocity if the initial velocity daw is negligible. So anong kukunin natin equation? We can get this velocity head equation to determine the final velocity. So paano? Since the initial velocity natin class is 0, so if this is 0, the initial velocity, it only leave us with HV or the static head, or sorry, the velocity head of air is equivalent to the final velocity or the outlet velocity raised to the second power divided by 2g. So pag siniro natin ito class, it will leave us with this equation lang. Do we have the velocity head of air? Makukuha naman natin yan based dun sa ating velocity head of water. Okay? So convert lang natin yung 0.0123 meters. This is head of water, velocity head of water into velocity head of air. So ito na yun class. It will give us 10.538 meters. Okay? So do we have the acceleration due to gravity? Binigay sa problem yan as 9.741 meters per second squared. Velocity head of air of 10.538 meters. Then one unknown, one equation, we can determine the outlet velocity of 14.328 meters per second. So, even though blower class yung naging discussion natin, gumamit pa rin tayo dito ng total head, velocity head, static head, and blower power using the total head. Correct? So, hindi pa tayo dito class gumagamit ng isentropic work. So, verify naman natin kung magagamit natin dito sa problem yung isentropic work. However, hindi natin pwede siyang gamitin kasi kulang yung mga binigay na properties. Okay? So, ganun yung approach natin class. Kapag binigyan tayo ng problem, verify natin dun sa given or i-analyze natin based dun sa problem kung ano yung approach natin, anong equation yung gagamitin natin. Okay, class? So, proceed tayo sa example 4.0. Pakita lang natin kung paano natin ginamit dito si isentropic work. So, a blower operating at 1,500 RPM compresses air from 65 degree Fahrenheit. So, binigyan tayo dito ng temperature. Binigyan tayo ng rotational speed. So, it compresses air from 68 degree Fahrenheit and 14.7 absolute pressure PSI. So, yung ating inlet pressure class is 14.7 absolute pressure. So, that is atmospheric or barometric pressure. Binigyan rin tayo ng inlet temperature of 68 degree Fahrenheit. Then, kinukompress daw niya to 10 PSIG. So, that is 10 PSIG meaning gauge pressure. So, convert natin yan later on into absolute pressure. So, that is the outlet pressure. 10 PSIG plus 14.7 is 24.7 absolute PSI. Okay? Then the desired flow is 1,350 cubic feet per minute. That is the volume flow rate. And at this point, the brake horsepower is 80 horsepower. Determine the overall blower efficiency at the design point if K is 1.3395. So dito class, binigyan tayo ng specific heat ratio of 1.3395. So pag ganyan, definitely may idea na tayo na isentropic work yung gagamitin natin. Okay? Isentropic work equation or formula. So pinapahanap is the overall blower efficiency, pero binigay lang sa atin is the brake horsepower, which is 80 HP. So going back to the equation, related yung class kay brake power. So yung pinapahanap lang naman pala sa atin is the mechanical efficiency, which is isentropic work over the brake power. Kasi nga, brake power lang yung binigay sa atin, brake horsepower, then no way na ma-determine natin lahat ng other efficiency. So yung mapoprovide lang natin is yung ating mechanical efficiency here. Okay? So i-term lang natin siya dito na overall blower efficiency. So anong equation yung gagamitin natin, class? So check natin kung magagamit natin yung equation na to. We have the value for K, correct? Do we have the value for mass flow rate? Hindi siya binigay, class. Walang binigay na density dito. Walang binigay rin na mass flow rate itself. So we cannot use this equation. Next, can we use this equation? Dapat, kasi wala na tayong option eh. So we have the pressure at the inlet. We have the volume flow rate. Pressure at the outlet, correct? 24.7 PSI. So we can use this equation definitely. Okay? So substitute lang natin yung mga given sa problem. So the K value is 1.3395. The inlet pressure class is 14.7 PSI. Convert lang natin siya into pound per feet squared kasi yung ating volume flow rate o ang ating blower capacity is naka-cubic feet per minute. So that is 1,350 cubic feet per minute. Let's cancel it. I'll give you 1 unit of feet. Then this 24.7, that is the outlet pressure. Binigay na rin tayo. Binigyan tayo nito class as 10 PSIG. Kinonvert lang natin into absolute pressure. Okay? So yung magiging unit natin dito after is pound-foot per minute. So that pound-foot per minute, mako-convert naman natin yan into HP. Divide lang natin into 550. So yung nakuha kong value dito class is 48.029 horsepower. Then that isentropic work, divide lang natin sa given na brake horsepower which is 80 HP para makuha natin ang efficiency. So i-multiply natin sa 100 and the value is 60% efficiency. Okay class? So for example 4.0, ginamit naman natin dito ang formula for isentropic work. So any question class before we proceed with our last example?
Wala naman po,
Wala pa
sir.
naman po.
Thank you. Sana na-gigets natin yun. And last example natin, example 5.0. So, ano lang to class, gagamit din tayo dito ng isentropic work, pero this is close, again, this is a good example. This is close to reality yung example natin dito. Pinapag-compare tayo. So it's a mixture of, may halo tayo dito na engineering economics. Kasi i-verify din natin dito, class, yung cost involved in installing different equipment such as turbo blowers or the variable frequency drive. Na i-compare natin yan dun sa existing na constant speed blower. Okay? So yung approach dito, class, is dapat madali lang kasi nga isotropic work lang siyang gagamitin. However, medyo kailangan natin ng konting analysis since nagpapa-compare dito or nagpapa-provide ng evaluation kung ano yung mas cost-effective or cost-efficient. Okay? So, i-explain ko sa inyo ng maigi, class, para mas maintindihan natin. Basahin natin yung problem. So, a facility has 3 existing constant speed positive displacement flow. So, take note, there's already an existing or installed 3 constant speed positive displacement blowers with 100 HP motors. So meron nang naka-install daw na 3 constant speed blowers. So the blowers were designed for the inlet pressure. So ito yung design parameters ng ating existing blower. Meron siyang, ang inlet pressure niya is 14.2 PSI absolute. The air pressure or the barometric pressure is 14.4 PSI absolute. And the discharge pressure is 9 PSI gauge. Okay, so that one will be converted later on into absolute pressure. And an airflow of 1,800 cubic feet per minute. So it is estimated daw na yung actual average airflow is 1,500 cubic feet per minute lang. And the current operating pressure is 8.5 psg. So sinasabi dito, class, na yung actual average airflow na nire-require ng system kung saan man naka-install yung ating blower is just 1,500 CFM. However, since constant speed to, meaning fixed drive, whatever happens, continuously and constantly magpo-provide siya ng 1,800 CFM. Kasi nga, hindi naman natin mababari yung speed ng motor, constant speed siya. So, 100% continuously magpo-provide to ng 1,800 CFM. Pero yung requirement lang pala, o yung actual average airflow lang naman na nire-require is just 1,500 CFM, meaning merong 300 CFM na overly or na po-provide ng ating fan na natatapon lang, na hindi nagagamit. Okay? So, those wastage equated siya sa cost of operation, sa electrical cost ng ating motor. Kaya ang isang option dito, class, we are given 2 options here. Yung first option is that to install a 100 HP constant torque rated VFD na nakakahalaga ng $15,000 ang installation cost. Alam naman natin na yung VFD, the variable frequency drive class, will ang kanyang purpose is to vary the speed depending on the required flow rate. Okay? So kung nagre-require lang ng 1,500 CFM, so pag nag-install tayo ng VFD, yung rotational speed ng motor natin, mababawasan yan para makapag-supply lang ng 1,500 CFM. And correspondingly, yung cost or yung operation cost ng ating motor will be reduced as well kasi nga hindi siya at peak capacity, hindi 100% yung kanyang rotational speed. Okay? So, i-compare natin yung cost reduction due to that power reduction as well, yung power saving ng pag-i-install ng VFD. So, pero, remember, or tingnan natin dito, yung cost ng installation is 15,000 din. So, isasama natin yan sa comparison. Magkano yung na-save at the same time, nagkaroon din tayo ng expenses worth 15,000 each. Kasi we have 3 existing blowers, tama? So, each blower, mag-install tayo doon ng VFD. So, 15,000 each blower, so times 3 yun, ha? Then, another option dito, class, is the installation of turbo blowers, which is $75,000 each. Medyo mahal si turbo blower kasi when installing turbo blower, meaning yung existing blower natin, existing motor natin, i-replace talaga natin yun, papalitan yun. Okay? papalitan yun ng isang set ng turbo blower. Meron na siyang blower, meron na siyang motor, meron na rin siyang VFD. Napakamahal nga lang niya kasi $75,000 isa. Tatlo yun. So, 75,000 times 3. Kapag nag-install para tayo plus ng VFD, i-retain natin yung blower, i-retain yung motor, mag-attach lang tayo or mag-install lang tayo ng VFD dun sa existing na motor natin. Okay? Kaya medyo lesser cost siya, $15,000 lang. I-assume daw natin yung efficiency ng existing blower as 65%. So, ilista ko lang siya dito class. So, existing blower, 65% efficiency. Existing motor is 94% efficiency. While for the frequency drive class, kapag nag-install tayo ng frequency drive, so ganun din naman, we have the existing blower kasi hindi natin pinalitan yung blower. We have the existing motor, hindi rin natin pinalitan yung motor, so parehas lang din. However, nag-install lang tayo ng VFD. So yung efficiency ng VFD natin is 96%. Okay? And the installation cost, lista ko na lang din dito, is $15,000. While kapag nag-install naman tayo plus ng turbo blower, ang efficiency ng turbo blower is 80%. Pag nag-install tayo nito class, i-replace natin yung existing na motor, existing na blower, and immediately magpapalit talaga tayo dito. So meron siyang sariling efficiency na. May sariling efficiency na yung blower na 80%. So that is definitely higher. May So merong efficiency yung motor, that is 98%. Relatively higher din siya sa existing motor efficiency. And yung sariling BFD ng ating turbo blower, which is 95%. So yung turbo blower pala class is just the whole package na to. Meron na siyang blower, meron ng motor, meron ng BFD. Kaya medyo mahal siya kasi lahat talaga papalitan. Okay? And the installation cost is around $75,000. Ngayon, ang hinahanap sa atin is to provide an initial evaluations to determine if it is more cost-effective to provide BFD for the existing blowers or to replace them with the high-efficiency BSD turbo blowers. The cost of electricity daw is 0.067 kilowatts. So, anong case natin dito class is that pinapa-compare sa atin magkano yung magiging savings or kung cost-effective nga daw kung mag-install tayo ng VFD or ng turbo blowers in exchange of i-retain natin yung existing constant speed. Okay? So, ang kailangan natin ma-determine muna dito is ano yung power consumption ng existing constant speed, then what will be the power consumption kapag nag-install ng VFD, what will be the power consumption kapag nag-install ng turbo blowers. Then, i-compare natin yung power consumption na yun, i-subtract natin yung nakuha nating power consumption ni VFD sa existing speed. So, existing constant blower, i-subtract natin yung nakuha nating power consumption ni turbo blower to sa existing constant speed blower. So, we have already the savings there. I-convert natin yan into dollars kasi ang tinatanong is i-determine ano yung most cost-effective. So, kailangan by dollars yung usapan or by cost yung usapan dito. So, hindi lang savings plus ang pag-uusapan, even isasama natin yung capital o yung ginastos natin during the installation. So, ano yung mas favorable at ano yung mas cost-effective between those two. Okay? So, by analysis, by calculation, i-estimate muna natin or determine natin yung power consumption ng existing constant speed. Ito nga yung magiging guide natin or basis natin kung magkakaroon nga ng power saving yung ating blower or yung ating turbo. Yung ating VFD or yung ating turbo blower. Okay? So we will be using isentropic work here class. So yung K natin, since hindi binigay sa problem, we will be using 1.4 as stated earlier. The inlet pressure is 14.2 psi. It was given here in the design. So the design inlet pressure is 14.2 psi absolute. So we need to convert. I-convert lang natin pala siya class sa pounds per feet squared. Okay? Inch squared. Then, The capacity or the volume flow rate nga natin is 1,800 CFM. Still 1,800 CFM kasi nga fixed drive pa yung pinag-uusapan natin, or ito yung constant speed class. So we will be using 1,800 cubic feet per minute. Cancel, cancel. Then the outlet pressure or P2 natin class will be 8.5 PSI gauge. Hindi tayo gumamit ng 9 PSIG kasi this is just the design pressure or the design outlet pressure. Rather, yung gagamitin natin class is the current operating pressure, which is 8.5 PSI gauge. I-convert lang natin siya into absolute by adding the barometric pressure of 14.4 PSI. So 8.5 plus 14.4 PSI, that will be the absolute pressure here. Okay? Then we can calculate now. So yung magiging unit natin dito class is pound-foot per minute. Convert lang natin into HP. And later on, convert natin into kilowatts. So bakit natin siya convert into kilowatts? Kasi yung ating cost ng electricity is $0.067 per kilowatt hour. So usable na gamitin or preferable na gamitin si kilowatt rather than the horsepower. Okay? So once we determine the blower power or the power imparted ng blower sa fluid, kailan natin makuha class ang kanyang power consumption. We can determine the power consumption by dividing that blower power into efficiency ng blower and the motor efficiency. So divide lang natin yung nakuha nating power dito or isentropic work into blower efficiency, which is 0.65, and motor efficiency, which is 0.94. So it will give us the power consumption of 69.7 kilowatts. This 69.7 kilowatts, by the way, ito na yung direct na naka-touch or ito na yung direct consumption natin plus na electricity. Ha? Hindi na siya yung ating isentropic work, hindi na siya yung power imparted to the air or gas. Ito na yung direct power consumption kasi i-divide na natin siya sa lower efficiency or dun sa mechanical efficiency, and divide na rin natin siya sa motor efficiency. Okay, so yung nakuha natin 69.7 dito, this is the power consumption na. So directly pwede na natin siya ditong calculate kung magkano nga yung nagagastos na sa konsumo ng kuryente using this power consumption. Okay. The next is to estimate the variable speed drive blower power consumption. So same equation, we will be using the isentropic work equation. However, yung babaguhin natin dito class is the volume flow rate or the blower capacity. As I said earlier, the actual average flow required is just 1,500 CFM, meaning there's a reduction of 300 CFM kapag nag-install tayo ng VFD. And correspondingly, it will affect as well the isentropic work or the blower power. So from 42 kilowatts, na-reduce yung work or yung power imparted to the fluid ng blower to 35.49 kilowatts. Okay, so meron na kagad changes pa lang. Ano pa lang to ka? Isentropic work pa lang. Then how much more kung i-calculate natin yung power consumption directly, since ito kasi is yung power imparted to the fluid lang, i-calculate natin class yung motor power, okay? O yung direct power consumption. So i-divide natin siya sa brake power or sa blower efficiency. I-divide natin siya sa blower efficiency, divide natin sa motor efficiency, and divide natin sa VFD efficiency. So it will give us 60.5 kilowatts. Okay, so there's a reduction of 9.2 kilowatts kapag gumamit pala tayong class ng VFD kung i-compare natin siya sa existing na constant speed. So magkakaroon kagad tayo ng 9.2 kilowatts. Not bad na, di ba? Kasi there's already a savings involved. Pero hindi yung magiging basis natin, i-convert natin yan later on sa dollar para ma-determine nga natin yung cost, kung cost effective to or hindi. And lastly, estimate or determine the variable speed single turbo blower power consumption. Since both of them have BFDs, so both of them will use 1,500 cubic feet per minute, and both of them will have the power imparted to fluid as 35.94 kilowatts. So parehas lang siya dito kay BFD class kasi parehas naman sila naka-BFD lang. Mag-iiba lang sila class sa power consumption kasi magkaiba na yung efficiency ng ating turbo blowers kaysa dun sa ating motor, blower, and VFD efficiency. Mas cost or mas efficient yung ating turbo blowers kung titignan natin. Yung blower efficiency is 0.8% compared sa 0.65% ng ating existing blower. Motor efficiency is 0.98% or 0.98 compared sa existing motor efficiency of 0.94. Correct? Kaya yung ating power consumption ng turbo blower is 47.65 kilowatts. So 69.7 minus 47.65 so meron ka agad na 22.05 kilowatts saving kapag nag-install tayo ng turbo blowers kaysa dun sa existing natin na constant speed. So medyo malaki, di ba? It's a great deal na kagad kung titignan natin when it comes to or when it turns to power saving. Pero yung pinapa-assess kasi sa ating class is determine if it is more cost efficient nga. Ano sa dalawa yung cost efficient. So even though malaki yung savings ni turbo blowers, i-consider din natin yung capital cost or kung magkano yung na-install or installation cost. So by that, determine muna natin yung cost reduction from the variable speed drive blower. So as I said, meron tayong savings in terms of energy na 9.2 kilowatts. Convert lang natin yan to how much yung save natin kada taon by assuming that the fan is in operation for 24 hours per day. So that one will be 9.2 kilowatts multiplied by how many hours per year? Kasi continuously na tumatakbo yung fan natin 24 hours per day. So how many hours per year? So it will be 8,760 hours kada taon. So multiply lang natin sa cost ng electricity which is $0.067 per kilowatt hour. So cancel. It will give us the savings kada taon in terms of dollars of $5,400 kada taon. So not bad na rin, di ba? Medyo malaki na in terms of savings. That is in terms of dollar na, hindi na in terms of kilowatt. So when installing the VFD, meron na pala tayong savings na $5,400 kada taon. Ngayon, kailan naman natin mabe-break even or kailan naman natin, kailan magkakaroon ng payback or mababawi yung capital na ginastos natin pag nag-install tayo ng VFD. So we just need to divide the installation cost which is 3 times 15,000 kasi plus tatlo yung ating blower, meaning tatlo yung motor, meaning tatlo yung i-install nating VFD. So 3 times $15,000 divided by the cost or energy cost reduction of 5,400 per year. So it will leave us 8.3 years. So yung 8.3 years plus within that span, diyan pa lang natin binabawi yung ating nagastos during sa installation ng ating VFD. So after 8.3 years, maganda na yung balita kasi we are starting to save na in terms of power and in terms of cost. Okay? So after 8.3 years, saka pala nagkakaroon ng savings. Then compare naman natin dun sa cost reduction or energy reduction when it comes to installation ng turbo blowers. So yung savings nga ng turbo blower is around 22.05 kilowatts. Okay? And that 22.05 kilowatts will equate to $12,941 per year. So twice yung cost saving ng pag-install ng turbo blowers, i-compare natin kapag nag-install tayo ng VFD. Pero the question is, kailan daw natin mabe-break even or kailan yung payback period ng installation ng turbo blowers? So same, divide lang natin yung total cost ng installation since tatlo ulit na turbo blower yung i-install natin. So 3 times 75,000 divided by the cost saving or cost reduction of $12,941 per year. So it will took us around 17.385 years plus just to break even or just to pay back yung nagastos natin nung installation. Okay, so medyo malaki or medyo matagal yung payback period kasi it will take 17.385 years pa para mabawi natin yung savings, yung installation cost. Then after that year pa, saka pala mag-i-start talaga na mag-save due to the installation ng ating turbo blower. So going back sa hinihingi sa problem, provide an initial evaluation to determine if it is more cost efficient to provide BFD or to replace them with high efficiency turbo blowers. So based from our initial assessment, both of them talaga is may cost savings, 5,400 per year para kay VFD and 12,941 per year para kay turbo blowers. However, kung ako yung mag-a-assign dito or kung ako yung mag-evaluate dito, mas ko consider class si BFD kasi for BFD, it will only take 8.3 years na maka-break even ka in comparison kay turbo blowers wherein it will take at around 17.385 years. So more than twice ng tagal ng operation ng ating BFD yung pag-i-install natin ng turbo blowers. Okay? After 8.3 years, nag-i-start na mag-save si VFD. While for turbo blowers, it will took you after 17.385 years pa. Okay? So that is our assessment on example 5.0. So hopefully class, clear sa atin yung explanation. Any question dito class?
So far, wala pa naman po.
Okay. So kung wala naman class, then ayun nga, please be ready sa quiz natin next week. So we will be having our face-to-face meeting, that will be our quiz. So yung scope nga nito is discussion natin ng turbine and discussion ng fans and blowers. Okay? So actually class, lahat naman kayo are 5 sections na hina-handle ko when it comes to fluid machinery, and all of you naman is sabay-sabay na mag-quiz. Yung iba nga lang by Saturday, yung iba by Sunday. Most of them is online yung quiz kasi wala kaming room pag Saturday, and kapag Sunday na umaga, ang available room lang talaga is sa inyo and yung sa tanghali. Okay? So napansin ko lang na hindi ko naman may iwasan na hindi sila mag-open notes kasi nga quiz yun and online, wala namang way para ma-prevent yun. So masasuggest ko class na yung quizzes nyo rin is i-open notes natin, okay? Para naman fair sa lahat. Pero when it comes to finals, when it comes to ulit-ulit na ako, when it comes to finals, major examination, bawal yung open notes natin, okay? So nagkataon lang na hindi ko mapiprevent na mag-open notes nga yung mga nag-quiz online. Hindi para fair lang, i-open notes na rin natin kayo during our quiz by next week. Pero yun, kung hindi naman natin naiintindihan on how to use those formulas, hindi rin natin matasagutan. So, ayun, please review our discussion ng turbines, please review our discussion ng fans and blowers, and please be ready para sa ating quiz next week. Okay, class?
Okay na okay po, sir.
Okay po,
Thank
sir.
you po.
Thank you po.
Maraming salamat po.
Okay, so for that class, see you next week, and please review our discussion. Thank you very much.
Thank you po, sir.